Now, at the end of class last time, or actually the entire class last time, we spent going over a kind of an exhausting blah, 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 blah presentation with a whole bunch of words and slides and of what this, of how the computer organization of the PEP9 CPU. And so what we're going to do today is going to be a little bit more lively. We're going to start right out with a demo. And the demo is going to be PEP9. And what you need to do is follow the link on the web page and to the book website, to the book site, and make sure you do the 5th edition and download the PEP9 and not PEP8. Okay, you guys, so here we have the PEP9 CPU app. And now I apologize, there are few little rough edges. This was just released a few weeks ago. And you'll notice that, and here's the register bank up at the top, just like we looked at last time. And the addresses of the registers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 for the instruction register, and 11 for temporary register T1. And you guys know, what should this be? That should be 12 and 13. So I have a little clip. We have a little glitch in our release here. So, and this should be 14, 15, and 16, 17, 18, 19, 20, 21. Is everybody with me on that? Okay, so when you use it, I think on the Windows side it's fine. This is the Mac version. And then these are, so those are the temporary registers. So here we have the accumulator, the index register, the stack pointer, program counter, instruction register, temporary register 1, T2, T3, T4, T5. And these M's are the read-only memory. So this is the 0, register 22 has a 00 in it, and register 23 has a 01 in it, and so on. All right, with these values in the register bank. And then all of this is what we went over in excruciating detail last time. But now, watch this. Now we're going to have, this is going to be nice and visual. So here's how the whole thing works. The whole thing works by taking, in one cycle, generally what happens is you put stuff on the A bus and the B bus, and you bring it around here, and you do some computation, and it comes up through the C bus, and it just comes back up to here. Are you with me? Now, and what we're going to do, just to, as our first little simple demo, we're going to just take something from, I don't know, let's just say we want to take, let's just take something from the index register. Here, let's put a value in the index register, like A, B in the index register, and let's try to, and let's move that, let's, no, I'll tell you what let's do. Let's put AB in the accumulator, and let's try to move it to the stack pointer, like move accumulator to the stack pointer. There's an instruction that moves A to the stack pointer. So let's just take this AB and try to get it to here. Now watch how we do this. In order to move it from here to here, first what we have to do is we have to put this on the A bus, right? So what tells us where to get the register to put on the A bus? It's this. Now watch. If we put a 0 here, or we can put a 1, or we can put a 2, or we can put a 3, or we can put all the way up to a 31. And as when you put that address here, what address do we want? What's the address of this AB? What's the register address of the AB? What is it? Hello? Testing, 1, 2, 3. Are there any people out there? What's the address of the right byte of the accumulator? The register address? 1, yes. 0 is the left byte. 1. So here, so we put 1 here. Are you with me? That's going to put that on the A bus. And now, what do we want to do? We want to make it go through the ALU up through here and put it in the stack pointer up here. So how do we get it? Oh, it's stuck here on the AMUX. How do we do the AMUX?
It's going to be the 1.
We want it to, now, it's going to be a 1, you're right. So how do we set it? Click makes it a 0, click makes it a 1, click makes it back to nothing. So it's a nice little three-way toggle. Is that slick? So there's a 0 and a 1. And now you can see that this is what's going through. Is that neat? And now we got to get through the ALU. But now how do we know what the ALU does? What can the ALU do? How many things, different things can it do? How many different things can the ALU do? How many? 16, yeah. And what determines that? The number you put here. That's the function, right? Yeah. So look, so you put 0, and look, it shows you right there. It shows you, oh, that sends A through. Here, if you do a 1, here, oops, if we do, here you have to type it. If we do a 1, it's A plus B. If you do a 2, it's A plus B plus C. And if you do a 3, it's A plus not B plus 1. If you do a 4, blah, blah, blah. If you do a 9, it's A XOR B. It shows you right there what it does. So what do we want it to do? Go straight through. So what was that? 0. And now what do? We got to get it to go through the CMUX. So how do we go through the CMUX? What do we need? What number? What value? Yeah, that's right. 0 is left, 1 is right. So 0, 1. And now it's being presented up here. And now what? Where did we say we wanted to put that?
In the 3 spot, right?
We wanted to put it right here.
Oh.
Yeah?
So in the 5.
In 5. So how do you suppose we do that?
Type 5 into the C box.
Yeah, so 5 is the address of where the C goes. Are you with me? Is this cool?
Yeah.
I think this is really neat. And now, after the cycle, we want to we need to have a clock pulse after that cycle. All right. So now, drum roll. If we clock this, what should happen? AB should go into SB. Boom.
Wow.
Is that neat?
That is really
Now, do you see how that works? Are we good?
That's really cool.
Now, how about we want it here? How about we have something? We put something in the program counter. Here, let's put like, I don't know, 2D in the program counter. Now, suppose we want to add 1 to this. How would we add 1 to this and put it back in the program counter?
So you would go through and
Yeah. Yeah. How are we going to? We want to add 1 to this 2D. Can you see?
yeah, 7 for A.
7 for A. Yeah, good call. 7 for A.
And then you're going to enable the mutex, the AMUX.
Well, before we do that, let's think about what else, because we have to add 1 to it. So what are?
Oh, I was going to add 1 in the ALU.
Well, you are going to add 1 in the ALU, but what is the?
Set B to 1, right?
Well, okay, you set B. That's not quite right.
Or
Yeah, why? You're right. Why is it 23? Because that's where the 1 is. Are you with me? That's the register address of the 1. Oh, you guys are good. Okay, are we good? And now what? You were going to say for the AMUX what?
1.
0, 1. So that will send. And now we have this here and the 1 here. Is everybody clear? And now what do we do for the ALU? Oh, we need to look it up, or we can just trial and error. Try 1. A plus B. Right? And no CN. Right? Now, actually, if we were going to do the high order bit, the high order byte also, we would also want to store the result, oh, what happened to all my values? I must have clicked, all my values went away.
Well, yeah, that's what happened to...
Cleared accidentally.
I think I cleared something accidentally. Okay, so let's do this again. So what was it for A?
A was 7.
7. B is what? 23. AMUX is 1. A plus B. And then let's deal with that later. And the CMUX is what? 1, and then it's going to become, and we want this to go back into the program counter, right? So that's what? 7. And after this whole thing is over, so it would clock this into here, and it would also clock something into the shadow carry bit if there were a carry. Are you with me? In fact, here we can make sure, let's set the shadow carry to 1 because there's not going to be a carry out. So the shadow carry should go to 0. Are you with me? So watch this. Clock. Boom, 2E. And the shadow carry the 0 was stored into the shadow carry. Yeah? Question?
Why did we have to do 23 for?
Because that's where we had, the question is, why did we have to do 23 for the B bus? It's because that's where the 1 is stored, the constant 1 is.
So it's always done kind of like by direct addressing?
Yes, good question. Yeah, that's a good question. All of these addresses, all of these numbers that we put on these lines are all register addresses.
Okay. Would it also be possible, say for T1, to put a 1 right there and then load 11? Or is it just better code to always reference 23?
Well, so the question is, T1 is simply just another register, so you can go from any register and combine any registers with any operation and put it to any register. Only thing is, you can't, if you put on C, if you put like 23 or 24, it won't change the read-only memory. Yeah, so otherwise you have complete flexibility. But I think the question was addressing modes here. Well, this addressing, the values that are on these 5-line addresses for C, B, and A, they are all register addressing, which you can think of as being direct. I think that's, somebody said direct. I mean, you kind of think of that as being direct addressing. But it's really just hardware. I mean, it's just, it's the address. We saw how the bus. All right, are you ready? Now, check this out. Obviously, there's not a little man inside the PEP9 CPU clicking all this stuff to do this stuff. So the question is, so now watch this. So what you can do is you can actually code what we did. So now, what was the first thing we did? What did we put on the A bus? What did we put on A?
7. Because that's the address of 2D.
So now, here's how you do it. So now we're going to actually program this. So A gets, what did we want for A bus? 7? 7. And now, what's the comma separator? Do you remember that? The comma separator in RTO? There's a comma and a semicolon. You remember that?
Is it sequential versus?
Yeah, comma is concurrent. So concurrent with having A be 7, what did we want to have?
B equals 23.
B equals 23. And then what did we want to have?
C equals 7.
Yeah, before we do that, let's kind of go through, before we do C equals 7, let's going through, what did we need?
AMAX.
We needed A, oops, sorry. We needed A mux equals what? 1. Then what did we need?
CMOX, or was that later?
No, ALU.
ALU. Actually, you can do them in any order. I'm just, or ALU equals what?
No, it was more than 1, right?
I think 1 was plus.
Oh, was it? Okay.
Yeah, I think it was A plus B. And then what?
In CMOX, or did we do shadow?
Let's forget the shadow for this
Yeah, so
demo.
CMUX.
For this demo, so CMUX was what?
1.
1 is correct. And then what?
So that's C equals 7.
C equals 7. And now, you guys, all that happens concurrently. Ready? And then in the end, after that data is all set, then we say what's going to get clocked. And so now we put semicolon. Are you with me? And then we do what?
Load CK.
Load CK. Right? Are you with me?
Does it matter where we put the semicolon and where the enter
Say it again, ask it again.
Does spacing matter?
No, spaces don't matter. Yeah, you can put spaces wherever. All right, and now what happens is,
Do we need to clock it at all?
well, okay, now up here we have a run and we have a debug. So if we run it, it'll just run through all those cycles. And if we debug it, it'll do one cycle at a time. But here, let's just run it. If we just run it, now what should PC be when we run this?
2F.
And there it is, 2F. You are right. 2F. But now you want to see something really slick? Watch this. Suppose you don't want to have to type all that stuff. Now here's a cool feature. Suppose you don't want to have to type all this. Watch this. What did we want for A?
7.
7. What did we want for B?
23.
23. What did we want for AMUX?
1.
1. And you can actually see it here. And for ALU we wanted 1. And for CMUX we wanted what? 1. And for C we wanted what? 7. And look this. And we wanted this local. Now look at this button down here. What does it say?
Copy the method back.
Now watch this. Are you ready for this? Drum roll. Boom. It writes it for you.
Wow.
It writes the code for you. And now when we do this again, what's going to happen? If we run this one again, what will it be? 3-0. Boom, 3-0. Is that a nice app or what? Yeah. Yeah. So now, and also I think with this app you can visually see what's being presented on the buses and what you need to do to route it to the different places. Now the one thing that we haven't looked at yet is how this interfaces with the main memory, but let's save that for a little bit later. Okay, end of demo. Okay, so that's our demo. And now what we're going to do is let's take a look at the microcode that we need to be able to write in order to actually implement the PEP9 instruction set at level ISA 3. And the first thing we have to do is we have to do the famous von Neumann cycle. And what are the steps of the von Neumann cycle? Fetch, decode, increment, execute, repeat. Right? If we don't remember anything in computer systems, we will remember the von Neumann cycle because it is the heartbeat of every computer, virtually every computer made today has this exact same von Neumann cycle in it. So here's a little slide that summarizes that. The cycle at level, now this is when we memorize fetch, decode, increment, execute, repeat. We were talking about at the assembly level, right? But now, as is true in all aspects of a computer system, there are details at a lower level that are hidden at a higher level. So when we said fetch, we said fetch the instruction at mem sub PC, right? The program counter is the address. But now what kind of instructions do we have at the assembly language level? There's two kinds. Do you remember what they are? There's two kinds of instructions. Do you remember?
2 and 3 byte instructions.
Oh, very close. Not 2 bytes and 3 bytes, but what? Anyone else?
1 and 2.
Well, yeah, some instructions are 1 byte. Do you remember what those are called? Yeah, those are unary instructions. And then non-unary instructions were how many? 3. Are you with me? Do you remember that? 1 and 3. Okay? So when we learned this von Neumann cycle at the assembly level, whenever you increment the program counter, the PC, you can increment it either by 1 or by 3. And on the next slide, we have a figure from chapter 4 that is how we learned the
Oh, the von Neumann cycle.
the von Neumann cycle in a pseudocode C-like language. And basically what we did in figure 4.31 back in chapter 4 is we would the way the process works is you first load the machine language program, and by the way, in PEP 9, where is it always loaded? Starting at what address? Do you remember where the programs always existed? Do you remember when you'd write a program and you'd put them in memory and we'd trace through them? Do you remember where we put the programs and the memory map? Yeah, at the top, you're right. Starting at address 0000. Remember that? We'd put them at the top. And then we initialize the program counter and the stack pointer, and then do, and then fetch, decode, increment, execute, while the stop instruction does not. Now, and how would we increment the program counter? Either by what or by what? Why do we increment the program counter? Yeah, so that it'll have the address of the 1 point. So what would we have to increment it by? Yes, either by 1 or by 3. And what would that depend on? Whether the instruction was what?
Unary.
Unary or not. Are you with me? So now, and those details are kind of hidden up there. But now what we see at this level is the cycle at level LG1, we have to actually figure out how to add to the program counter. So the instruction could be either unary or non-unary, and if the instruction is non-unary, then we've got to get, you know, those buses, the A bus and the B bus and the C bus, and all those fat pipe looking buses, they're all just 1 byte. So we're either going to have to get 1 byte from where? When we fetch from where? Into the CPU. Where do we fetch from? No. Where is the program stored? In the system. No. Where did we say the instructions are? When we load, when we come back here, go to the previous slide. When we load the machine language program, that's loaded from disk into where?
Oh, memory.
Into memory.
Yeah.
At what address? 0000. So here, whenever we fetch the instruction, where do we fetch it from? From memory. But we can only fetch how many bytes at a time? Because our buses are only 1 byte. Just 1 byte. So we're either going to have to fetch what? 1 byte, and then we'll be done, or we fetch the 1 byte and we discover that it's a what? Non-unary instruction, in which case we have to do what?
Fetch another.
Fetch 2 more bytes. Are you with me? Because the PEP 8 data bus is only 8 bits wide. Are you with me? So here in figure 12.4 is a more detailed, now these details are hidden at level ISA 3, but now they're visible for us because we're down here at the lowest level, right? So let's see what we have to do for the von Neumann cycle. First of all, we fetch the instruction specifier at the address in the program counter. Then we do what? What does it say here? We do
Increment
PC by 1. Okay, PC gets PC plus 1. So we decode, and by the way, where does it pull it? It pulls it from memory into which register in the CPU? Do you know? It pulls it into where in the CPU? There's a register that it puts the instruction in. Do you know what? Which register does it put the instruction in? It must be the instruction register. It must be the instruction register. All right? And then once it's in there, yeah, high five, fist.
Yeah.
Okay, and then once it's in there, we can decode it. At that point, we can figure out whether it's what? Whether it's unary or not. If it's not unary, then what do we have to do? If the instruction is not unary, we have to do what?
You need to grab 2 more.
Yeah, you fetch the high order byte, and then PC gets PC, because the PC has been incremented, so that's the address of the
last one.
of the first byte of the instruction specifier. And then once we get that byte, we get the low order byte, and PC gets PC plus 1 again. And then, so in total, you see by this code that PC will either be incremented by 1 or by 3. Yeah, question?
How large is the instruction register?
Good question. The question is, how large is the instruction register? And it is
2 bytes.
3 bytes to take into account that you might have to store 3, but sometimes it doesn't use the last 2. On a unary instruction, it just uses the first byte. But there's 3 bytes. If you actually, we'll see here in a second again how big the instruction register is. And then we execute the instruction fetched, and then we do that while the stop instruction does not execute and the instruction is legal, because there might be some illegal addressing modes, you know, in the native ISA3 instruction set that cause the whole system to hiccup. All right, now this next sequence of slides we can go through pretty quickly because we already demoed what we're saying here. So each line, you saw when we wrote the code, each line is a clock cycle, comma is the parallel separator, semicolon is the sequential separator. Remember we had the clock's pulses at the end. Control signals before the semicolon are combinational signals set for the duration of the cycle. So you remember when all those colored, when the data was being presented, it was going through all those, remember for example, the ALU is a combinational device, not a sequential device. So just a few gate delays, and then after all those gate delays, the data is at the entrance of the sequential circuit that we want to clock it into. All right? And then the control signals after the semicolon are the clock pulses at the end of the cycle. Are you with me on that? And so now we didn't demo, we did not demo how to get something from the memory into the CPU. So now we're going to do, so now how do we do a memory fetch? So here's how to fetch from memory. Now what did we say is the meaning of MAR? What does MAR stand for?
Memory address register.
Excellent. It's the memory address register. And what does MDR stand for? The memory data register. So address register and data register. Are you with me? The address registers are connected to the address lines on the system bus, and the data register, MDR, is connected to the data lines on the system memory bus, right? And here's the thing. It always takes longer, more than one cycle, to fetch something from memory. So in PEP 9, it takes 3 consecutive cycles. What you have to do is you have to put the address in the MAR. Are you with me? You got to put the address in the MAR. And you have to have, and then you have to have the memory read line asserted for 3 consecutive cycles. That gives enough time for the data to be put on the to be put on the system bus. And after that, on the 3rd cycle, then you can clock the information into the memory data register. Are you with me? Now, here's figure 12.2 again. Let's see if we can figure out how to fetch from memory. Are you with me? Fetch from memory. Now, and what is where? The program counter has the address in memory of where we want to fetch, what we want to fetch. So here, let's see if we can, so here comes, let's go around the room. All right? Who wants to go first? We saw that code that we wrote before? You know? So tell me, here's the first question. How do we get the content of the program counter into the MAR? Now, why would we want to do that? Because what does the program counter have in it? The address of the next instruction. So do you see that we have to put the content of the, now this is a big concept, we have to put the content of the program counter into the memory address register. Are you with me? Now how would we do that? Looking here, Do I have the exploded version? No. So how would, looking up here, what do we have to put where? Yeah, now look, here's another thing. We want to, yeah, see what we want, remember there's two MARs, there's a high order and a low order. So we want the high order of the program counter to go to MARA and the low order of the program counter to go to MARB. Are you with me? So how would we do that? So who wants to, okay, you must, so A equals 6, all right, and then CJ, and then B equals 7, all right, and so that will put, and now they will be presented in the MAR, right? And now in order to clock them into the MAR, what do we have to do? Next. I don't want to say your name because this is for public. Oh, you want to? Oh, yeah.
Or we would have to set the MAR CK?
Yes, MAR clock. MAR. So that will clock those into the. That will clock those into the MAR.
Where's the MAR CK on?
Yeah.
It's right here.
Oh, okay. Got it.
Yeah, all of these signals are, this is, the control section is on the right, all the control lines are coming from here. Are we good? Okay. And then what did it say we had to do 3 times in a row?
Clock at 3 times.
Well, we don't clock it 3 times. What we have to do is we have to assert a memory 3 times. Do you see what I'm saying? Because it takes time. Now that address is on there, and we're going to say our memory read, we've got to go 3 times to. So this is going to be a mem read. I'll just do this one. Mem read.
Do they all have to be on separate lines?
Yeah, now that's a good question. Do they all have to be on separate lines? The answer is yes, and the reason is because each line is one cycle. Are you with me? Each line is one cycle. And at the end of this cycle, we know that the data that's on this address is where? We know that it's going to be presented here. And so now what do we have to do to clock it into the MDR?
Enable the MDR box.
So MDR mux gets what?
1.
MDR mux equals 1, comma, and then what? Or is that all? And then what? And at the end of the cycle, we want to clock it into the MDR, right? So MDR, oh, should it be 0?
Because we're going from the left.
Oh, you're going from the left. Oh, you're right. Correction. 0 because it's coming from the left. And then at the end of the cycle, what do we want to clock it into where? Clock it into where?
MDR.
MDR. So how do we do that? So semicolon and then what? What always comes after the semicolons?
Equal. So MDR equal.
No. What's always after the semicolons?
MDR clock.
Yes. Because so it's being presented, and then at the end of the cycle, that's the one. That's you're saying which one is going to be clocked in. So this would be what? MDR-CK, right? Is everybody clear? Now we have to get that to where? Yes, we have to put it on the C bus and into where? The instruction register. And what's the address of the instruction register? Way up there at the top. Yeah. So, here's 5. So now what? Now how do we get it onto the C bus? Do you see a path?
Yeah.
Do you see a path? Through the what?
Mux. up.
Yeah. Yeah, see how this is just plumbing? It's just plumbing. You just see where do you want the water to go. Okay, so what do we do? So now what goes?
We want AMUX equals 1 or 0, right?
AMUX equals 0. Does that take it from the left? Is that what we want? Yeah. And then where is it going to go?
ALU.
Through the ALU. Now, do you remember the function that passes it just straight through?
0.
It was 0, right? So it's ALU equals 0. All right, and then what? It's got to go through where?
CMUX.
So what do we make that?
CMUX equals 1.
Boy, this pen is drying out. Oh, that's much better. So CMUX equals 1. We want it to go to the right, or from the right. And then what? We, yeah, and why that? Because 8 is the address, is the register address of the first byte of the instruction register. And then what? And what do we want to do at the end? CK. Oh, load CK. Yeah. Let's see if we did it right. Oh, and we haven't done PC gets PC plus 1. We'll do that next time. But did we do the first 5 correct? Everybody see how that? Did we do it right? Okay, so we're going to end this with a demo. Now watch this. We don't have to type all that stuff out because why? We go to the help system and look at this. We go to figure 12.5, which is that program that's in the book. All the programs that are in the book are here. And we can just do what? Just like your old PEP 9 app. Just do what? Copy to microcode. Has been modified. You want to save your changes. Don't save because we don't care. And look, our program is all right here. What we wrote. Are you with me? And if we want to single step through this, watch this.
Oh, wow.
Start debugging. And look, it puts it just like you would put it here. Are you with me? So check this out. So what do we have? 7 and 6. Is that what we said? Mm-hmm. See? So the code that's here, gotta put my glasses on. A equals 6, B equals 7, MARCK, right? And so we single step through. Oh, one more thing. We also have this unit pre. If you look right here, what it does is it initializes memory sub 00FF to AB. So it puts something in memory so that we can know, so that we'll have something to move to the instruction register. Okay, so it initializes. If we scroll down here, if we scroll to 00FE, see, here's 00FE and here's 00FF, and so we're going to, and notice that the program counter is FF. So it's going to fetch from this location in memory. Are you with me? So now watch. We'll single step here, and so we'll single step this, and what happens? Boom, so there's the FF, is in the address, are you with me, is in the MAR. And now 3 consecutive steps. We got to scroll here to see the mem read here is being asserted. So we'll single step another one. And now when we do the third one, guess what happens? It's ready to be in, okay? And so now we're going to do the MDRCK. And so what should come up into this MDR? Prediction, what should come up into here? Nope. Say it again. Well, there is a 00, but when I single step, and when we do memread MDR mux equals 0 MDRCK, what should come into here? AB. It'll come from memory over the data bus into here. Are you with me? So let's try it. Boom, and there's the AB. Does everybody see that? And now what's going to happen is The AB is going to come through here and up through here, and C is going to be 8, so it's going to go into here. So here, one more, and we're done. And there's the AB, so we did the fetch. All right. We'll continue this madness next time. Oh, that can't be right. Figure 4.31. Now I'm going to have to clip that out. I'm going to change the slide. And, anyway. Okay, now what did I say this figure should be? So is this even a figure? I remember now. Shoot. Oh, I thought I made a mistake and I was right the whole time. Okay, so now we got to go back and, okay, take two.
Take two.